So this is another torque and equilibrium problem, and you should stop and pause the video, digest the problem, maybe draw a quick sketch of what you think is going on there. But this is a little more complex than the last one I've solved, especially because we now have forces at angles, and especially because we are asked to find the force exerted on the beam. And you can't read these yet, and you're not supposed to, but it's going to sort of break down into 3 equations, and those are represented in these 3 groups as part of the solution. But arguably the most important part of the solution is to first draw a good picture of what's going on. So when you draw each individual force in this situation, you can see that you have to first select a pivot point, which I've selected right here. Now, the strategy in selecting a pivot point is usually that you want to select a point where you know there either, I was going to say there's not so much that there's no force acting, but that it's a force that's acting but you don't know what that force is. And since that force is being multiplied by 0 moment arm or 0 lever arm, that force will not be relevant to any of the equations. So although there's a force here at P from the wall, we don't need to know what it is yet. We can figure that out later. Here's my angled tension force from this rope right here. Here's my force weight straight down. And if you're wondering what that's from, it's really assuming that the weight from the beam is acting right from the center of the beam right here. And we know it's acting from the center of the beam because of this word here. It's uniform. It's a uniform beam. So the weight acts at the center. The 800 Newton force acts at this end of the beam, the full length of the beam away. So our picture, we're going to refer to that constantly now. Now, the main equations, and it's a new equation in this unit, is that you know that the torques that are counterclockwise equal the torques that are clockwise. So the clockwise torques, if you think about it, are these the torques caused by these 2 forces, because those would tend to rotate it clockwise. Now, even though this is an equilibrium situation, these forces would have a tendency to rotate it clockwise with this selected pivot point. And the forces that are counterclockwise are, well, really only one force. This is the force that would tend to rotate it counterclockwise. So what you then do is you put the RF in for each of those forces. So this is the R for the 600 newtons, which is, it's hard to read, but that's an L over 2 right here. Okay, this right here is an L over 2. And then we have the 600 Newton force. And then we have L, where this force acts. It's hard to tell because it's crossed out, because algebraically I'm going to cross out all the L's later. But we don't know the beam length, but we just call it L. And then this is the force that is acting at that point. Then for counterclockwise, the force is this tension force, and the tension force is acting at 3/4 L, as indicated here, 3/4 L. So the tension force is unknown, so we just write Ft, but it's a little more complicated than that. It's I'm putting the sine 40 in there because we have this 40-degree angle right here. And that 40-degree angle tells us that not the entire force is actually acting as a torque, it's only the perpendicular component. And that perpendicular component, I'll draw it right here in red, but this perpendicular component right here is really the part of the force that we care about in terms of torque. Now, I plug and I chug and I cancel out my L's. Don't forget this right here is an L over 2, and this is an L, and this is a 3/4 L. Plug, chug, cancel out your L's, and you end up with a force tension of 2,282 newtons. So that gets me the tension. Now, on to the question of how do I figure out the individual, it says the components of the force that are exerted on that pivot point, on that hinge. So to figure that out, I'm going to say two things. Number one, that the force up equals the force down, and number two, that the forces left equal the forces right. So what I'm highlighting here are these two equations. The force up equals the force down, right here, the force up equals the force down, and the force left equals the force right. Okay, well, let's look at the up-down stuff first. The force up consists of the upward part of this tension force and this F sub h, which I'm calling the force from the hinge at that pivot point. I don't actually know what direction it is, but I'm just going to assume it's up. We don't know. We'll see. The force is down. Well, I know I've got my force weight down, meaning the force weight of the bar, the beam, and the force weight 2, which is this downward force. I know the up has to equal the down. I solve for the force on the hinge, and you get negative 66.6. Well, the fact that it's negative tells us, well, we guessed wrong, it's actually down, so we just say 66.6 newtons down. And look at this. If you look at this, what you get when you do the tension times the sine of 40, clearly it's more than the combined weights, so we need more upward force. Now let's look at the forces in the left-right axis. Go get him, David. And in the left-right axis, we have tension cosine 40, because we're taking this tension right here and we're now interested in the horizontal component. So that's times the cosine of 40. And now the other force is the horizontal force to the right at this point. If you think about it, the wall can only be pushing to the right, horizontally speaking. You solve for F sub h and you get 1,748 newtons to the right. So that's the solution, and to summarize, you want to focus on three main equations. The clockwise torques equal the counterclockwise torques up here. Clockwise equals counterclockwise torques. Forces up equal forces down. And forces to the left equal forces to the right.